that kind of want to highlight for you guys is that in our text, this is the CATS text, table 12.2 has the rotational versus translational motion.
It counted that right for the first part.
It did?
So it's
Okay. Okay. That's what I'm thinking. So I'm thinking I think we're on the right track. So yeah, it has rotational versus translational motion. So that's where that table is. So it's a handy table for you guys to be looking at. And on Monday, we showed that theta was S over R and that R theta was equal to S. We showed that V was going to equal R omega. We showed that A was going to equal R alpha. And this one right here is tangential. Okay, so that's a key that it's tangential. So if I'm looking at my circle, I'm going to have an acceleration that's tangential to the circle. And I have my downward or center seeking acceleration, which was the centripetal. So something that you've got to remember is I've got two parts. So my acceleration total on my particle that's traveling around this thing is going to be, the magnitude total is going to be the translational squared plus the centripetal squared. Because you have two components that you're worried about, the center seeking acceleration and the acceleration that's going around. So let's look at my centripetal a little bit, just so I can look at it from a different point of view. And that, if you remember, was V squared over R. And if I plug this in there for V squared, I get R omega squared divided by R. And I can actually rewrite my centripetal acceleration in terms of my angular velocity. So something to kind of think about when you start working these problems. And I'm guessing I don't have homework for this chapter out yet, right? I don't. So I get to add that to my to-do list. I get to totally add that to my to-do list. So hopefully by Friday it'll be up. I'm not promising anything. The way this week is going, I am not promising diddly squat. Okay, so we've got that one there. So now, when we look at this, so let's look at our lovely planet Earth. Now remember, we're kind of a squatty planet, but we're going to assume that we're a nice uniform planet. We're also going to assume that we're looking at the planet through its normal axis. We're going to spin our planet, because that's what we do. Our planet is actually spinning. So the first thing to think about is what is the angular velocity of the planet. We can calculate it, can't we? What's one complete cycle? Okay, it's 24 hours. Time-wise, it's 24 hours. What's the distance? One complete cycle. We're in radians. So what's the difference? 2 pi. Don't make it harder than it is. So I got 2 pi, but I want this in seconds down here. So I got to convert 24 hours into seconds, right? So if I convert 24 hours into seconds, it gives us something like 8.64 times 10 to the 4th. So it's 24 hours. There are 60 minutes to an hour. And there are 60 seconds to a minute. So we get like 8640 seconds. So my angular velocity of our good old planet, if I do this, it's 7.3 times 10 to the minus 5 radians per second. So we can actually calculate our angular velocity. Now, what is our angular acceleration? It's sort of a trick question. Our angular acceleration. So we're looking for what is alpha for the planet. So if I do this, if I'm doing a change in angle is going to equal my initial times time plus 1/2 alpha t squared. Think through it. What is my angular acceleration of the planet? Now, because we are us, there is a little bit of error. But was today longer than yesterday? No. Was yesterday longer than the day before? So am I changing the angle in a 24-hour period from day to day?
No.
So what does the angular acceleration have to be in order for that to be true? If this is equal for day 1, is equal for day 2, day 1, day 2, if that equation is true, which it is, what does the angular acceleration have to be to make this work? Come on, folks. I know it's 1:30 in the afternoon, but if that's going to be the same, that's going to be the same. What does that part have to do?
0.
It's got to be 0. It's got to be 0. So by observation, our planet isn't accelerating. At least we hope not. It could get very, very bad. Could get very, very bad. So our angular acceleration is 0. We're sitting there rotating at a constant angular velocity on a day-to-day basis. Now, granted, our year is sucky, and so we do have to throw in and fix our clock every now and then. But as a general rule, we don't change the time of the length of a day on any given day. That's good, in 24 hours. Now, sunlight's a different story. And sunlight changes because of our tilt towards or backward from the sun as our places in our orbit. Sunlight's a different story. But the actual how we're doing is not. So let's look at our good old planet again. So we're going to look at a point on the equator. And then we're going to look at a point on our planet where this angle is 40 degrees. We want to know the distance, the linear distance that this point travels in one day. And we're going to want to know the same thing there. This is the implication of latitude. So I got my lovely planet. And if I'm doing this, this is our nominal Earth radius. And the nominal Earth radius is 6.37 times 10 to the 6th meters. So that's this. But this is going to be something different. That D, because we're going to compare these 2 points, D is going to equal R cosine of the angle. And so that's going to be my 6.37 times 10 to the 6 meters cosine 40 degrees is going to give me 4.88 times 10 to the 6 meters. So my change in distance in a 24-hour period is going to equal my change in angle times my radius. And my change in angle is 2 pi because I'm in radians. And my radius is going to be 6.37 times 10 to the 6th meters. This is for on the equator. And that's going to give me 4.00 times 10 to the 7th meters. If I do the other one, I still am only going through 2 pi, but my r is different. And that's my 4.88 times 10 to the 6 meters, which is going to give me 3.07 times 10 to the 7 meters. Now, if I want to know the velocity that these things are moving, the linear velocity, that's going to be r omega. Well, we figured out what omega was. So this is going to be my 6.37 times 10 to the 6th meters, and my omega was 7.3 times 10 to the minus 5 radians per second. So that's going to give me, if I do that, and I plugged it into the calculator, this gives me 4.6 times 10 to the second. For the other one, if I do my 4.88 times 10 to the 6th, and if I do that, that's times my 7.3 times 10 to the minus 5, this is going to give me 3.6 times 10 to the second meters per second, and that's meters per second. So our tangential, the whole idea about this right here being 0, that means my acceleration tangential is equal to 0. But I do have a center seeking one. That's my centripetal acceleration, and I can go ahead and calculate it that way. And just plug in the numbers and can do the comparison. Now, this one, the way we've done that calculation, if I'm looking at it, this is going to be the acceleration towards the center line, not the acceleration towards the center of mass. All right? So the numbers aren't going to work out to be 9.8 meters per second. This is related to just the rotational motion that we're going around the circle. Okay, and it's actually going to be a small number. So let's do one just for grins and giggles. So if I do my 6.37 times 10 to the 6th, 7.3 times 10 to the minus 5, it's going to end up being 3.4 times 10 to the minus 2. And that's meters per second squared. So this centripetal acceleration comes from the fact that if I'm looking at it from a top-down point of view, okay, I'm looking from my merry-go-round. So here's the center. This is where my axis is. This point is moving around this way. This is the centripetal acceleration towards that. That is just because I'm moving around in a circle. Remember, my acceleration due to gravity, this little g, is related to the universal law of gravitation, the mass of the Earth, the radius of the Earth squared. So I have a little bit of a different type of an acceleration that's happening in one place versus happening in the other. This is just related to the motion. But this is going to be how I'm going to get artificial gravity. That's why I spin the space station. Okay? That's why you might spin a satellite to develop that artificial gravity. Okay? Well, I am not going to start anything new because I would be about to start levers and looking at rotation around levers. Levers. Time for torque. Torque. Good stuff. Time for torque. Yep. So we will see you guys on Friday.